particle has an anti-kind of particle. So a neutron has an anti-neutron, a proton has an anti-proton, an electron has an anti-electron. This does not mean that every single proton has its corresponding anti-proton. Let's say that there are 10 protons in the universe. That does not mean that the universe has 10 anti-protons. One of the enduring mysteries in physics, which you'll probably get a Nobel Prize if you solve, is why is there an asymmetry between the amount of particles versus antiparticles in the universe? If the number of particles and antiparticles were exactly the same, we would not exist. For this reason, that if you bring a proton and an antiproton together, they annihilate, they completely destroy each other and 100% convert into energy. So the average nuclear bomb and atom bomb, my understanding is it may convert about 1% of its mass into energy. And you can see how destructive that is, right? About 1% of its mass gets converted. Is it a question?
Yeah. So protons are positively charged.
Yes.
Electrons are negatively charged.
Mm-hmm.
So it says that antimatter is the opposite charge.
Yes.
So an antimatter proton would essentially act as an electron.
Oh, I see. Good point. An anti-matter proton would be an anti-proton that purely based on charge would behave like an electron. However, its mass is substantially greater. It's like 2,000 times the mass of an electron.
Yeah.
Right? Extra credit for the question. Right? Now, so the antiprotons are negative and they also are antimatter. So if you bring an antiproton and a proton together, they will just completely, flash of light, complete conversion into energy. Same thing with a positron. A positron is the antimatter equivalent of an electron. So if you bring a positron and an electron together, they will annihilate, just a flash of energy, and there's no matter left. We miss you.
Sort of on that note, the opposite happens, right? What happens to a neutron?
Same thing.
Are there anti-neutrons?
Yes.
So it's no longer neutral.
Okay. A positron is positively charged to match the fact that the electron is negatively charged.
Right.
The neutron is it's neutrally charged. There's no charge.
Right.
And similarly, the anti-neutron is neutral.
Remains neutral. Okay.
Yes. So together they are neutral, right? So positrons basically this is antimatter particles, the equivalent of electrons, but antimatter, are used nowadays not uncommonly in hospitals and so on. If you ever heard of PET, positron emission tomography, right? Which is a way of telling, like, if you have cancer or something like that. It's one of multiple ways. Basically what they're doing is that they may be imaging your brain or something like that by sending a beam of positrons into you and looking at the behavior of the beam, right?
So if every atom has protons and electrons, how do they use, how is there not explosions then in the house? That doesn't make sense. How do you have antimatter and contain it if it's reacting with, I mean, there's nothing that's made
Correct.
that doesn't have, I don't understand that.
Good question. Extra credit to you. Next question.
So we don't know, is that what you're saying?
No, actually, with positrons, what happens is we can generate the beam of positrons, and in order to use it, typically you try to contain it in a evacuated chamber. So like a glass chamber that is evacuated. Let's say there's no air in it. So a positron beam can do its own thing until it hits something, right? Can do its own thing, and it's not contacting any matter. If we were to send a positron beam through this room, which is full of air, what will happen is pretty soon the positron will hit an atom and it will annihilate and give off a photon, basically a gamma ray.
It would be like almost instantaneous.
Yes.
There's atoms.
That's correct.
So
Good
it
point.
will give off a flash of light because it's pure energy.
It'll give off a gamma ray. It'll give off a gamma ray which is like light. Light is electromagnetic radiation. The gamma ray has a higher energy than normal light does.
Okay, so what would that look like to the human eye?
To the human eye, you probably won't see anything.
Okay.
Or
Just 'cause
if
it's
it hits,
so small? If there were a bunch
because
of them
it's-
reacting, we would see something, but
well, it has to do with the detection capability of the human eye. Think of the retina. The retina has certain chemicals in it, rhodopsin, I forget what it is, like certain proteins, that what happens is when a photon comes, it's totally amazing. It really is totally amazing how it works. The protein has a certain shape. When a photon comes and hits the protein, it changes the energy of one of those atoms, which then changes the shape of the protein. And that triggers a very complicated sequence of events that sends an electrical signal down the fiber to your brain/mind, which then interprets that as light, as a photon. So a gamma ray, in principle, could trigger something like that in your eye. But the odds are that the gamma ray, its energy it doesn't match the energy that's needed to get the reduction or whatever the protein is to absorb it and then change shape. Right? I'm sorry? Yeah, you do not want to look at a laser.
I used to work with fiber optics, and you can't really see the color of the laser, but it still does damage to your eye and it gets spots.
Yes, yeah. If you look at a laser, then but that could be because of heating and stuff like that, right? The energy is being like once it hits the retina, the energy is absorbed, and it'll just blow your the proteins apart, and so you can get permanent blindness, right, as a result of that. Okay, extra credit for speaking up, extra credit for the question. Okay, next thing is dark matter. It looks like, like in science, a lot of times when we don't know something or don't understand something, we just throw up basically everything in science. We think we understand something because we put a label on it, right? So particularly if we don't know, have no clue what it is, we put a label on it, and that makes us feel better about not knowing anything, thinking that we do know something about it now, right? So the rather strange thing is, somewhere between 95% and 98% of the mass in the universe, we don't know what it is. It's completely, we don't have a clue what the mass is. The universe behaves as if its mass is 20 times larger than what we're able to sense, either through looking at stars or looking at normal like planets and all that kind of stuff, right? The remaining stuff in the universe is believed to be some form that we don't have any clue what it is. So because we don't know what it is, and because we're not able to see it, we can't see it, touch it, feel it, taste it, whatever. So, for lack of a better term, they just call it dark matter. So, for whatever that's worth. Okay, so a reminder for you guys to go over the multiple choice questions, right? Once the lectures are done.